2.5, polynomials with complex zeros. The first thing we need to address is the imaginary unit. We just call it I. I is equivalent to the square root of -1. Meaning, if you took the square root of -1 and multiplied by the square root of -1, then the squares would cancel and you would just get -1. So I squared equals -1. Now, we all know that that's problematic because you can't take the square root of a negative. However, this is how we deal with those situations. So, really, ultimately, what happens is when you see this negative underneath this radical, we just bring it out and make it I multiplied by the square root of what's underneath it. Okay? Complex numbers are what we call the numbers that have imaginary components. However, I do need you to keep in mind that every number can be written as a complex number. For example, 7, you could just write as 7 plus 0i. It has 0 imaginary part, but that way it's in the complex format. Okay, so keep that in mind. We also need to talk about what we call the complex conjugate. And the complex conjugate is just the exact same thing as that 0 complex number where we had a plus bi, except for that the sign in front of the I term has now switched. You'll notice a stays the same, but the sign in front of the I term is the opposite. That's what we call a complex conjugate. So let's jump into dealing with some i's. So when we want to simplify I squared, well, that's -1. By definition of what I is, I squared is -1. Okay? Then if we go to b, the first thing I see is, oh, there's a negative under the radical here. So we're going to take it and we're going to bring it out as an I. So this says 7 minus I times the square root of 144. Well, of course, the square root of 144 is 12. So we can just say 7 minus 12i. For c, we have a -6 here. I also see this negative, so I'm going to bring it out as an I, but we still have the square root of 64 here. And these are all just multiplied by each other. Of course, the square root of 64 is 8, so -6 times 8 times I is -48i. Okay. When we have two of them, we just do the same thing. We're still going to pull it out in front. So this is going to be I times by the square root of 9 times by I times by the square root of 49. Well, I times I is I squared, which gives us -1. The square root of 9 is 3, and the square root of 49 is 7. So we're going to do -1 times 3 times 7. Well, that's just -21. So then we have this one, and we treat it just like a variable. We go ahead and distribute in. So 5 times 3 is 15. 5 times 4i is plus 20i. -I times by 3 is -3i, and -I times by 4i is a -4i squared. Anytime you see an I squared, you should immediately go, oh, that's a -1. So really, this is a -4 times by a -1, which is just a plus 4. So now we have some like terms here. 15 plus 4 is just 19. And 20i minus 3i is just 17i. So there you go. For f, something similar happens, but we have to remember that this means 4 minus 7i multiplied by 4 minus 7i. And then we go ahead and distribute. 4 times 4 is 16. 4 times -7i is -28i. -7i times 4 is still -28i. And -7i times by -7i is a plus 49i squared. Again, anytime you see that, you should think, oh, that's -1. So really, this is a -49. Then we can combine these like terms. So 16 minus 49 would give us a -33. And -28 minus 28 gives us this -56i. So it's just a matter of combining those like terms. For complex conjugates, All we have to do is change the sign in front of the I term. So the complex conjugate of this z, 9 minus 4i, is 9 plus 4i. That is the complex conjugate. Now it also wants us to find the product of the two. So we're going to do 9 minus 4i multiplied by 9 plus 4i. And this works the exact same way. We're going to distribute. 9 times 9 is 81. 9 times 4i is plus 36i. Negative 4i times 9 is a minus 36i. And negative 4i times 4i is a negative 16i squared. Oh, there's that I squared again. So really, this one is plus 16. And I want you to notice these two cancel. That should always happen in a complex conjugate. If it didn't, we probably found our conjugate incorrectly. So if those two cancel, then we're just left with 81 plus 16, which is of course just 97. And you should just get a whole real number when you do complex conjugate multiplication. This example is a quick reminder of both the fundamental theorem of algebra and the conjugate pairs theorem. So the fundamental theorem of algebra says that whatever the degree of the polynomial is how many roots, zeros, solutions, whatever you want to call them, that it should have. So this one should have 2 roots. The conjugate pairs theorem says that imaginary numbers come in pairs. Complex answers, or zeros, come in pairs. Because if a plus bi is a 0, its complex conjugate is also a 0. So let's do this example. So this one doesn't factor. So we are going to use the quadratic formula. So the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So this is going to simplify down to 4 minus 20 divided by 2. And of course, 4 minus 20 gives us this negative. This is where this all comes in, because now we're trying to take a square root of a negative number. And as you guys know, that doesn't work unless you're dealing in terms of imaginary numbers. So then we've got 2 plus or minus I times the square root of 16, which is 4. So 2 plus or minus 4i divided by 2. And of course, 2 divided by 2 is 1, and 4 divided by 2 is 2. So this one we can go ahead and reduce a little bit. So 2 plus 4i over 2 is going to become 1 plus 2i. Similarly, we're going to end up with 1 minus 2i. So here are our 2 roots. You'll notice they are complex conjugates of each other. That should always happen. Let's do another example where that works. With these examples, some of them it makes sense to use quadratic formula. Others it makes more sense to factor. It just depends on the problem. So let's go ahead and jump into example 4. Grouping will absolutely help us here, because this leaves us with x squared multiplied by x plus 1 plus 4 times x plus 3. Oh, oops, that should be a 3 too. I'm sorry. So then we can get that x plus 3 multiplied by x squared plus 4. Okay, now x squared plus 4 does not factor. When it says to get it to an irreducible quadratic factor into linear or irreducible quadratic factors, this is what it means. We can't factor any further. Now, this doesn't mean we can't find the zeros, though. So this one's 0 would be negative 3. This one, however, we have to do a little bit more work to get there. So we're going to have that x squared equals negative 4. So then x equals plus or minus the square root of negative 4. So of course we got to bring that negative out. So we're going to get plus or minus 2i. Now remember, we started this with a power of to the third. So we should have 1, 2, 3 solutions. And in fact we do. So our solutions would be that x equals negative 3, x equals negative 2i, and x equals positive 2i. Let's do another one. So this one has an x to the 4th. There should be 4 solutions. I'm going to go ahead and use u substitution to try and work this one out. So u equals x squared, and u squared would equal x to the 4th, which leaves me with u squared plus 52u plus 147. I'm going to be honest, guys. I cheated ahead of time and found what this one should be. Okay. but I am cheating. You should use the quadratic formula to do this. But I know that this factors into u plus 3 multiplied by u plus 49. Okay, I wouldn't have known that. I would have used quadratic formula on this. Nonetheless, here we go. We're going to set that equal to 0, which means that u can be negative 3 or u can be negative 49. Well, but u is just x squared. So x squared is supposed to equal negative 3 or negative 49. So when we take the square root here, well, we get the square root of a negative in both cases. So we need to pull those negatives out as I. So we're going to have plus or minus I times the square root of 3. And then this one would be plus or minus. Now, 49 is a perfect square, so we're going to pull our 7 out, and we're also going to pull our negative out as an I. So our 4 solutions here, they are all complex in this case, are plus or minus I root 3 and plus or minus 7I. But it does want us to have it in either linear or irreducible quadratic factors. So now we have to figure out how the heck to write these. So this one's kind of weird. Remember, though, that factors should be x minus something. Well, I need to do x minus a negative I root 3. And I also need to do x minus a positive I root 3. And I need to do x minus a negative 7i. And I need to do x minus a positive 7i. So what ends up happening is that this, of course, becomes a plus because we're minusing a negative. So we're going to have x plus I root 3 as one factor. This one doesn't have anything to cancel, so it just becomes x minus I root 3. Minus a negative gives us an x plus 7i. And then the last one is x minus 7i. Okay, so you could have left it like this. However, technically these are not irreducible quadratics or linear, right? So we would actually want to multiply these together now, which is kind of complicated, but we can do it. So x times x is x squared. Here we get a minus ix root 3. Here we get a plus ix root 3. And here we get a minus I squared and a root 3 squared, which is 3. But again, I squared is negative 1. So we really have a negative 3 times by negative 1. So we're actually going to add 3 here. And the two middle ones, because it's a conjugate, should go away. So this factor is actually going to be x squared plus 3. And we do the same thing over here. X times x gives us that x squared. We're going to do minus 7ix, but then, of course, we're going to add a 7ix back. And we've got a negative 49i squared, which, of course, should tell us that's actually a plus 49. These two cancel, and we end up with x squared plus 49, which, had we done this problem a little bit differently, we actually could have already known. If instead of solving for it right here, I could have just plugged x squared here and here. I wanted to do it the long way to show you guys how to do it, but you actually already had the answer. Last example in this section, there really is no good approach to this, so we resort to our p's over q's. So the choices for our factors of p are 1 and 7, and the choices for our factors of q are 1, 2, 3, and 6. Plus or minus 1, plus or minus 1/2, plus or minus 1/3, plus or minus 1/6, blah, 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 blah. There's a whole bunch of them, right? The easiest way to do this is with our synthetic division to see if we can find something that gives us a zero remainder. So I always like to start with 1 and negative 1, just to see. So if I do 1, that's going to drop down a 6. 6 times 1 is 6. Okay, so that's not giving us a zero remainder. Okay, so it's not 1. Cross that off my list. Let's try a negative 1. Okay, certainly not -1 either. I'm noticing that I got some really big numbers at the end there. So that tells me I probably want to deal with a fraction instead. So let's go ahead and try it out with like maybe 1/2, because that's next on my list. So let's drop our 6. That makes 3. Makes -17. 15. 7. Oh, perfect. Okay, so remember though, this means 6x to the third minus 34x squared plus 30x plus 14. So if it looks like you might be able to factor by grouping here, you can stop doing synthetic division and do that. Doesn't look like that's going to be possible in this case, so I'm just going to keep going. I usually like to try 1/2 again, but I know it doesn't work in this case, so I'm going to go ahead and try 1/3. Okay, I don't like that one because I'm getting a not whole number. So what if we actually tried -1/3? Perfect. Okay, so again, this is really telling us 6x squared minus 36x plus 42. And I'm like, oh, those are all divisible by 6. So I'm going to pull that out right now. Okay. And this 6 is actually really important because it's what gets rid of our denominators in these two factors. So remember, this is saying that x minus 1/2 has a 0 and that x plus 1/3 has a 0. But I also have this 6 out here. And in fact, what we're going to do with that 6 is we're going to split it into a 2 and a 3. And then the 2 goes to the one with the half, and the 3 goes to the one with the 1/3. That's how we get rid of those fractions. So we're going to go ahead and distribute that in right now. And distribute that in. So we've got 2x minus 1 and 3x plus 1 as 2 of our factors. Now we can just deal with this x squared minus 6 plus 7. Most of my students want to be like, oh yeah, that totally factors. But it doesn't, because -7 and 1 do not multiply to a positive 7. So we're going to have to go ahead and do the quadratic formula on this one again. So it equals the opposite of b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. So this ends up as 36 minus 28. So 36 minus 28 is 8. And this is where it comes in handy to know that plus or minus root 8 is 2 root 2. Because 6 divided by 2 gives us 3. 2 divided by 2 gives us 1. So this is 3 plus root 2 or 3 minus root 2. As far as writing our factors out, we can just pull this -6x plus 7x squared over here. Those are all of our factors. But it also wants us to actually state the zeros. So the zeros would be 1/2, -1/3, 3 plus root 2, and 3 minus root 2. Our last section has to do with building a polynomial given some factors and or information about this. So it tells us that the zeros of p are c equals plus and minus 2 and plus and minus I. So this tells me right here that x plus 2 is a factor and x minus 2 is a factor. Okay. Now the c plus or minus I also tells me that x plus I is a factor and x minus I is a factor. Okay. This is interesting though because it's still actually x minus minus 2 that gives us this one, and then x plus a -2 that gives us this one. So keep that in mind when you're doing these, that the signs are changing. We also know that the leading term is supposed to be 42x to the 4th. Well, that makes sense with our x's because here's 1, 2, 3, and 4, but we need a 42 on here. So you can just throw it out in the front if you'd like. However, you cannot leave these i's here. You need to go ahead and multiply those in. So x times x is x squared minus ix plus ix here minus I squared, which of course is minus a -1, which is plus 1. So we are going to end up with a 42 times by x plus 2 times by x minus 2 times by x squared plus 1. So then when we have this, this is our irreducible factors, okay? And then when we have these irreducible factors, we can be done. We just need to make sure that our a is where it needs to be. Now it tells us that the polynomial is degree 3. Remember, that means we're going to have an x to the third. It has real coefficients and zeros at x equals -7. So this would be this factor. And x equals -3 plus 3i. Okay, so that would be x minus -3 plus 3i. X plus 3 minus 3i. But that also tells us one of our other zeros, because we would also have -3 minus 3i as a zero because of the complex conjugate theorem. So this one is x plus 3 plus 3i. And you'll notice that the sign in front of the 3 doesn't change. It's only the sign in front of the I that changes. So now we're going to go ahead and multiply all these out. And this one is a little bit more complicated. So we've got x squared plus 3x plus 3ix. This one, we've also got a plus 3x here. And I like to line those up top to bottom. 3 times 3 is 9. I'm going to put that somewhere new because that's a new type of term. And 3 times 3i is plus a 9i. Now we've got -3i times x. I'm going to put that under there because those are like terms. -3i times by 3 is a -9i. And -3i times 3i is a -9i squared. However, I know that a -9i squared is -9 times by -1, which is really a plus 9. We get that we have an x squared plus 6x. These two cancel. These two cancel. Plus 18. And we still have our x plus 7 hanging out. Now, the only other thing we know is that if we plug a 0 in, we should get a 252 out. What we're doing here is we're saying, okay, f of 0 needs to equal 252. So I'm going to put a 0 in here. So 0 plus 7 is 7. 0 squared is 0, plus 6 times 0 is 0, so that'll just come out as an 18. So that is a times 126 equals 252. 2. So what this tells us about our polynomial is that it needs to be, f of x should equal 2 multiplied by x plus 7 multiplied by x squared plus 6x plus 18. And that is the polynomial that we needed. So now it gives us a graph. So the polynomial is degree 4 with real coefficients that has a 0 of x equals -1 minus I, and the absolute value of the leading coefficient is 1/14. If we have a 0 at x minus 1 minus I, that means we have an x minus a -1 minus I as one of our factors. And we also have an x minus a -1 plus I as one of our factors. So this is really x plus 1 minus, plus I. And this one is x plus 1 minus I. To go ahead and multiply those out, x times x is x squared. X times 1 is x. X times -I is -ix. 1 times x is x. 1 times 1 is 1. 1 times -I is -I. I times x is plus ix. I times 1 is plus I. And I times -I is a -I squared, which is a -1, which is truly a plus 1. So then we get that we have x squared plus 2x. Those cancel, plus 2. Okay. However, we know that this has a polynomial of degree 4. But we also know something else. We know we have a 0 at 2. Sorry, -2, which gives us this. And I hope you can see how wide this is here. It's because this has a multiplicity of 2. Now, I know it's 2 because the total has to be 4. It's got to be even because it just bounces up. I already have 2 from here. 1 would have just gone straight through, so it has to be 2 there. Okay. We also know that the leading coefficient needs to be equal to the absolute value of 1/14. Well, I know that this one should be positive because it goes up. It hasn't been transformed to reflect across that x-axis, so it should stay as a positive 1/14. This one wants us to have a degree 3 with having real coefficients having zeros of 5 and 2i and a leading coefficient of 1. So a 0 at 5 looks like this. A 0 at 2i looks like this. And remember, we always have our complex conjugate also. So x times x gives us that x squared plus 2ix minus 2ix minus 4i squared. That cancels. That's really a negative 1. So this comes out to be x minus 5 multiplied by an x squared plus 4. And then we know that the lead coefficient is 1. And we know we should have 3 degrees. So 1, 2, 3. That's done. So now it wants us to find a degree 3 polynomial. But we have zeros at negative 2. So that gives us x plus 2. As well as 1 plus 7i. So that's x minus 1 plus 7i here. As well as x minus 1 minus 7i. And this comes out a little bit simplified here with a minus 7i. And this one is a plus 7i. So when we multiply that together, we've got an x squared minus x plus 7ix. We've got a negative x, a positive 1, and a negative 7i. Our last term to distribute in, negative 7i times x is a negative 7ix. Negative 7i times by negative 1 is a plus 7i. And lastly, we have a negative 7i times by positive 7i, which comes out to a negative 49 times I squared, which is really a plus 49. So these cancel. We're left with x squared. And then we've got plus 1 plus 49, which is x squared plus 50. And we still have our x plus 2, of course. Now let's go ahead and deal with the end behavior. So this is saying that as x gets bigger, y is going down. So as we are going this way with x, y is headed downward. But as x goes this way to negative infinity, y is headed upward, which tells me that I have an odd coefficient, right? We're going this way and this way. And because of it being quote unquote backwards, I also know that it needs to be negative. Okay? So I need a negative out here. That's it.